Designing for earthquakes has always been one of the main challenges in structural engineering. As researchers in earthquake engineering, we try to develop new ideas and innovative structural systems to have a positive impact on both structural performance as well as construction and repair practices. A crucial part of these developments is to test these ideas with accurate and reliable experiments. And one of these experimental methods is the, so to speak, pseudodynamic hybrid test method. Similar to most simulations, in hybrid simulation, most of the structure is modeled numerically, but the critical component of the structure which absorbs the seismic energy is physically represented in the laboratory. We refer to it as the physical substructure. This enables our experiments to have a much better correlation with real earthquakes. In our research group in recent years, we have shifted our attention towards multi-element hybrid simulations, where instead of only one or two substructures, we can test several in order to increase the accuracy and effectiveness of the experiments. As part of this initiative, the UT10 was recently developed in our research group as part of my supervisor's long-term vision to achieve hybrid simulations that include the largest number of physical specimens than any previous cases in the world. Currently, we can do hybrid simulations with up to 10 physical substructures using the UT10. The system consists of 60 hydraulic actuators in a very unique configuration, which allows for flexible reconfiguration of the experimental test setup to accommodate testing of different systems and different structures. We recently did multi-element hybrid simulations on a 4-story steel structure designed with cast steel yielding connectors, also known as the Scorpion yielding connector, which is a state-of-the-art cast steel energy dissipative device developed and commercialized by CastConnex. We designed and detailed the building and basically wanted to analyze the structure in the principal axis of interest. The seismic force resisting system in this direction consists of 4 identical concentrically braced frames with cast steel yielding connectors, where one of the frames was isolated and studied in the hybrid simulations. The 4 yielding connectors were physically represented in the UT10, while the rest of the structure was modeled numerically in the OpenSees. This was the first multi-element hybrid simulation where we physically captured the response of all the nonlinear components in the seismic force resisting system, and was a true application of a novel testing method in an efficient way. The results of these experiments demonstrated a uniform classification of the structure along its height, which is a signature response of the cast steel yielding connector for mitigation of soft story formations. The unique results of these experiments will serve as benchmarks, which would allow us to better calibrate our numerical models, understand the low cycle fatigue life of cast steel elements, and were a stepping stone towards further development, verification, and application of novel testing methods.